All right, so the purpose of my 3 talks will be to explain, if you want to reach open questions, but which have to do, of course, with the theory of toposes, and which, if you want, they are intimately related to the primes, to the spectrum, if you want, of the ring of integers. And the specific topic which triggered my talks is, at first, if you want, the link between theory of nodes and prime numbers, which was, which is an analogy, if you want, and which was first put forward by David Mumford and Barry Mazur around 1963, and which, if you want, is based on the fact that, when you think about spec Z as a scheme, right, and you look at it as a topological space, it doesn't look very promising, because what it is, it's just a collection of all primes and the generic point. Now, the generic point is very special because it's everywhere dense. But one major contribution of Grothendieck, which is, if you want, very much the starting point of the theory of toposes, is the discovery of the Idele site. So in fact, what I will start by doing is to explain to you the Idele site for the scheme, which is spec Z. And somehow, if you want, this Idele site already enriches considerably the structure. And then what one finds out by doing some computations, which were done by Michael Artin at the time, and Verdier, is that the spectrum of Z looks a bit like a 3-sphere. And the primes, the primes appear inside as some nodes, as analogous to nodes. So, since this is a school and I don't want to, rush through things, so today will be simply the story of the analogy between prime and nodes. Tomorrow will be the role of class field theory and if you want, the main contribution to this topic that we have with Katia Consani is, in a sense, the extension of class field theory. So if you want, class field theory is a theory which computes, or if you want, gives you the Galois group of the maximal abelian extension of a global field. Now, it's an extremely beautiful theory, and however, it's a theory which concentrates on groups, on Galois groups. Now, if you want, the version that Grothendieck gives of Galois theory, even of Galois theory itself, is finer than just looking at groups. When you look at books on Galois theory, usually you just talk about groups. And there is a very striking fact, which is that the deepest result in Galois theory do not deal with groups. They deal with group acting on sets. And in particular, there is an amazing result that Galois stated when he was 17 years old. So what Galois wrote when he was 17 in a paper is that for an equation which he called primitive to be solvable, a necessary and sufficient condition is the following, is that you can label the roots of the equation by the field FQ. So in particular, it means that the degree of the equation is the prime power. And then what Galois wrote, what he wrote is that then the Galois group of this equation has to contain the translations, because of course it's acting transitively on the roots, and it has to be contained in the affine group, of FQ, semi-direct product by the Frobenius. So Galois knew about the Frobenius, okay, and then one has understood Galois only about I think it's in 1957. It was done by a mathematician by the name of Huppert, and he understood what Galois meant by a primitive equation. Because Galois was extremely obscure in his writings, and people had tried to understand what it meant, and what Huppert has understood is that what Galois meant was that the Galois group is doubly transitive in the set of roots. Okay? And of course, as you can see, this is a notion which uses not only the group, but the action of the group on the roots. Okay? And then Huppert was able to prove the theorem of Galois with a few exceptions. The few exceptions are for Q equals 3 square, 5 square, 7 square, 11 square, 23 square, and I think it's 3 to the 4th, something like that. Okay, so I mean, and Galois knew that there were exceptions. Okay, so the reason why I start like this, I really want to strike you with this fact that it's just not groups, and this would be a central theme. Okay, so the second thing which you are not necessarily supposed to understand or to know, and even if you know, it's not clear that you really master it, is why do we bother about this notion of scheme when we are talking about rings, okay? So if you want, you have commutative rings. And I mean, at first, if you're a little bit naive, you will think that it's a luxury to talk about schemes, because after all, what does it do? It takes the category of rings and it just takes the opposite category, okay? Now, the real reason why schemes are so important, if you want, from the very start, is again an analogy. And this analogy was put forward by André Weil. And if you want, you have three texts in this analogy. So you have Z, okay, or rings of integers in a number field. So this is the first thing. Okay. Then you have another one, which is, if you want, smooth curves over a finite field. Okay. And you have a third one, which is compact Riemann surfaces. Okay. Now, so what André Weil explains in a lot of convincing terms is that these three things are analogous, they are text, okay? This is perfectly well understood, okay? Thanks to transcendental methods mainly. This is rather well understood as well, and this is still mysterious. But what are they? They are all examples of regular schemes of dimension 1. Okay. So once you know this fact, you can accept the notion of scheme, okay? Because it unifies together all these various aspects, okay? All right, so if you want now a fundamental contribution of Grothendieck is the understanding of Galois theory, but if you want, the extension of Galois theory to schemes. So we shall explain that. So if you want, when you have a scheme, you have a connected scheme, otherwise you have, I mean, there is always the problem of the choice of the base point, but this problem will not be crucial for us because we shall use the abelianized fundamental group. So this, I want to not spend time on this problem. So what you have is, if you want, there was in the 50s, in the Cartan seminar, it was clear to many people that there was an analogy between Galois theory and coverings of a space. And in fact, Dixmier told me the anecdote that once, I think it was Pierre Samuel, who was saying that this analogy doesn't work for some reason. And then Henri Cartan interrupted him and told him, you are wrong. And he explained that the analogy is perfect, okay? Now, as turned out, Serre at some point found a very interesting example of an algebraic variety, smooth, which is defined over a number field, which is not Q, okay, so it's defined over a number field. And when you look at the complex variety, of course it will depend on the way you embed the number field in the complex numbers. In general, there is not one way to embed the number field in the complex numbers, there are several. And what Serre gave, he gave an example where the corresponding complex varieties that you get has a fundamental group which is different in the two cases. So not only they are not homeomorphic, but they are not even homotopic. So this meant, if you want, that the idea that you can understand an algebraic variety just by looking at the complex points is wrong, okay? Now, the great contribution of Grothendieck concerning this problem is that, in fact, again, by listening to a talk by Serre, which Serre was giving in the Chevalier seminar, I think in '57. And in fact, Chevalier was not present when Serre was giving his talk. So Grothendieck understood that the notion that Serre had devised in order to restore the local triviality of a bundle when you deal with algebraic groups. So Grothendieck was in the room, understood that this was giving the correct definition for the topology that he was missing, which was purely algebraic. And this definition, so we shall come back to that, uses, so if you want, the problem with this definition of the étale topology is that if you are a mathematician and you are not persistent enough, you can very well get totally discouraged from the beginning by the complexity of the definition. So I will give you a very simple definition, okay? And this definition is like this. You need, in order to understand the definition, to understand the notion of what is a separable algebra. So separable algebra, it's an algebra over an algebra A, so it's an algebra B over A, which is extremely simple as a module over A because it's a free finite free module over A. But that's not enough. What you want is that the trace map, which the trace of course is well defined for matrices, and when you have a free module like that, every element of the algebra now B gives you a matrix because it's a multiplication by B. Everything is abelian, so there is no question of left or right multiplication. So it gives you a matrix, and you can take the trace of this matrix, and using the trace of this matrix, you get a map, okay? You get a map, which is a very natural map, which goes from the algebra B to the homomorphisms of array from B to A. Now, we say that the algebra is separable when this map is an isomorphism. So you can say, oh, wow, come on, I mean, it will always be the case, you know. But just look at the example of an nilpotent extension, namely when you look at the algebra which is obtained by adding x but with x squared equals 0, then, you know, we are mathematicians, we are not listeners, we are actors. So the only way to understand things is to act. So just pick this example and do it by yourself, okay? Understand by yourself why this doesn't work in this case, all right? Now with this definition, okay, then the definition of a finite étale morphism, which is all you need in order to define the étale site and the corresponding topos and everything, is like this. It imitates exactly what happens when you take a cover and that this cover is locally trivial. You see, when you take a cover of a space and you say that the cover is locally trivial, what does it mean, a finite cover? It means that over small enough open sets, you will have a stack of copies of this open set. So here it's the same, but you want to be a bit careful and you want to have this notion of separability, otherwise it wouldn't work. Okay? So you have this. All right, so this is the definition of a finite étale morphism. Okay, and now an exercise for you in topos theory is to define, using this notion of finite étale morphism, to define the étale site corresponding to this notion of finite étale morphism. Okay? All right. And once you have this notion, okay, in fact, you don't even need the site for that, we can come back to the Grothendieck-Galois, the extension by Grothendieck of the Galois theory. First of all, why is it an extension of Galois theory? Well, it's an extension of Galois theory because if you take the scheme X to be the spectrum of a field, all right, then again, exercise show that in that case, all right, what you get is exactly the Galois group of the maximal separable extension of the field. Okay? And the notion of separability for fields, not every extension of a field is separable when you have a characteristic P. In characteristic 0 it is, but not in characteristic P. And then you will see that you come back exactly on standard Galois theory. Okay? But there is much more interesting situations. And the really much more interesting situation now has to do with the ring of integers. And to understand what happens with the ring of integers, you have to understand what is ramification. To understand ramification, again, you can look in books, you can take Wikipedia and whatever, and look, okay? But until you do it a bit by yourself, you will not get it, all right? So what is ramification? What is the simple idea which is behind? The simple idea is the following, is that if we take an algebraic number field, which is a finite extension of Q, all right? So let's take such an extension of Q. Now, we can think of it as being given by giving a polynomial, P of x, okay, and adjoining the roots of this polynomial, all right? Okay, but if we do that, what will happen? What will happen is that, you see, the example which I gave you of an algebra which is not, this example which I gave you just before of this algebra which is not separable. Why isn't it separable? It's not separable because there is a double root, okay? So the obstruction to get something nice is to have double roots. Now, if you have a polynomial, P, the double roots are governed by the discriminant of the polynomial, which is just, if you want, the product of the difference between the roots. But then you raise everything to the square. And that's computable in terms of the symmetric functions, so it's computable. It's called the discriminant. Now, this discriminant, if you take a polynomial like this, you can assume it's non-zero. Yes. But if the polynomial is defining an algebraic integer, it will be an integer, this polynomial, this discriminant. Okay, so it will be an integer, delta belongs to the integers. Okay, and being an integer, it will be divisible by some primes. Okay. Now what will happen is that if you look over this prime, then it will look like your polynomial will have a double root. And this is where ramification appears. It's a little bit more tricky than that. Okay. It's a little bit more tricky than that, and for that you have to do again an exercise. Okay. And I ask you whether 2 is ramified in z of square root of 3, and whether 2 is ramified in z of square root of 5. Okay. And please don't look in books, don't look in Wikipedia and so on. Just think about it yourself. Okay. Now, so the point now is the following. The point is that given all this, we can start the analogy between spec z and, if you want, between the primes and the nodes. Okay. And so there is this ramification. Okay, so there is a general way to compute the Idele fundamental group, which, okay, I mean, it uses a little bit of mathematical vocabulary. So there is this notion of being normal, integral scheme. If you want to see a scheme which is not normal, you look at the equation y squared equals x3. Okay, that's a curve which is defined by this equation. This is not normal. The reason why it's not normal is that when you take y over x square is equal to x, and there is no element in the ring which is y over x. Okay. So okay, you have to at the same time do exercises and learn vocabulary. Okay. But very important thing is that you get motivated to do the exercises. Okay. So there is this general way. So there is a way, if you want to compute the Idele fundamental group, going back to Galois theory and looking at the function field of the scheme, right? So you can use this tool. Okay, so now let me go to the analogy. Okay, so the analogy goes as follows. So first of all, the scheme spec z, but now endowed with the Idele site. Yes. So now, if you want, there is a magnificent theorem which was conjectured by Kronecker and which was proven by Minkowski. This is called the Minkowski bound in algebraic number theory. And this magnificent result is that any algebraic extension, finite algebraic extension of the rational number, ramifies somewhere. Okay, so there exists a prime at which it ramifies. Now you could be tempted to say, but it's trivial because you told me that we have this discriminant, and so this discriminant is necessarily divisible by some prime. No, it's not trivial. It's not trivial at all because there are nuances on the definition of the discriminant. So it's not trivial at all. And moreover, I mean, the Minkowski bound is used in many other situations. Now, what does it mean? What does it mean with the new vocabulary of the schemes, okay, and of the Idele site of the scheme? What it means is really that spec z is simply connected, okay? Because you cannot find a non-trivial cover, okay, which is unramified everywhere. So that's the first fact. Okay, but there is much more than that. And there is much more than that. There is, so let me erase here. Yeah. There is much more than that. There is the fact that, which was discovered by Artin and Verdier, if you want. And so we shall have to enter into the guts of this fact. All right? So what is this fact? It tells us that H3 of the spectrum of Z with coefficients in the multiplicative group is Q mod Z. So let me explain that. Okay, so first of all, what is this GM? what is this GM? Okay. So this GM, what it is representable sheaf. Okay. In other words, if you want, it is given any ring, for instance, you can take on of Z of T and T inverse with values in A, where A is a ring. And of course, this is just the invertible elements of A star. Okay, so that's the first point of what is GM. The second point is the generic point of spec Z. Generic point eta of spec Z. Spec Z viewed as a scheme and so on, okay. So it's a very strange thing. In fact, the idea of defining the spectrum of a ring using not maximal ideals, but prime ideals, okay. In fact, this idea was suggested to Grothendieck by Pierre Cartier. In fact, it's really Pierre Cartier who is at the origin of this idea. And the reason why he suggested it is the following, is that when you take morphisms from one ring to another, it's not true that when you pull back a maximal ideal, it will always be a maximal ideal. That's wrong. But it works with prime ideals. Now there is a very bizarre prime ideal. Okay? When you take Z, the ideal is 0. And it's prime. But you can see that any open set in spec Z, which is not trivial, which is not empty, contains this prime ideal. You just have to do a little bit of mental exercise, okay, to understand that any open set contains this prime ideal. And so it's everywhere dense. So it's extremely bizarre, okay? Nevertheless, you have a map J, from this to spec Z. Okay. And then you can do the following thing. You can consider an exact sequence where you take if you want, the GM for spec Z. Okay. And I mean, this goes to the GM, if you want, for eta. But this is pushed forward by this map J star. So if you want, it's like J star of GM eta. Okay, and you get something here. And what do you get here? You get exactly the Cartier divisors. Okay? So you get this exact sequence. So what is the idea of Cartier? It's in fact an idea which comes from the theory of Henri Cartan of analytic geometry, from the A and B theorems of Cartan. And the idea of Cartier is that to define a divisor, well, of course, you could define a divisor in a very trivial way by saying that you give a certain number of points and you give integers for these points, when in the case of curves. But what Cartier says is that no, what you have to do is to consider the function field, because this is what happens when you take the GM eta. When you take the generic point, the sheaf that you have is just a field, and it is the function field of Z, so it's Q. So what you do is you take, if you want, the non-trivial elements there, okay, in fact you can go even to the algebraic closure, and you take now the quotient by the things which are invertible in Z. And that's enough to give you the notion of Cartier divisors. All right, so now what you do is you use this exact sequence, and you use it at the level of H2, okay? So and there will be a connecting map which goes to H3, and we shall come back to that at some point. But the very important fact is that when you look at H2, this is something again which I have to explain in very, very simple terms. When you look at H2, let's look for instance at H2 for this term. So H2, so it's H2 of this all right, with coefficients in GM then. So what does it mean? What is the meaning of this H2? Well, the meaning of this H2 is the following. I presume that you all know quaternions. You have seen quaternions somewhere, okay? Now, let me tell you what they have to do with H2, all right? Okay. So, when you look at the quaternions, all right, what I am saying is that quaternions, they are just the semi-direct product of C by the Galois group, Galois of C over R, but twisted by a cocycle. Twisted by a cocycle. So in other words, you see, the point is that quaternions, they are given by ijk, all right, where I square is -1. Of course, all of these have square -1. And what the J does, the J implements the complex conjugation on the complex numbers of the form A plus BI. So if you take J, A plus BI, J inverse, this is equal to A minus BI. So the J is implementing the complex conjugation, but the J doesn't have the square that you would wish it to have, which would be 1, because complex conjugation, the square of it is the identity. So square of J is not 1. Square of J is -1. Okay? And in fact, this -1 is a 2 cocycle. It's, so I wish you to think about that. Okay? So you have a 2 cocycle. It's a 2 cocycle from the action of the group Z mod 2Z, which is the Galois group of C over R, okay, acting on R. And you cannot untwist it, because when you try to untwist it, the numbers that you get by trying to untwist it are numbers of the form Z times Z bar. Now the numbers of the form Z times Z bar, they are positive reals. So you're stuck, okay? So we have a non-trivial cohomology class. Now in general, when you look at the H2 in the middle here, what you have is you have Q bar, the algebraic closure of Q. And you look, if you want, you try to imitate this construction. And so what you try to do is you try to define quaternions, but in order to define quaternions, you look at central simple algebras, or rather skew fields. Now, you could say, well, it's strange to look at skew fields. But again, a very, very instructive exercise is to do the following, is to show that when you look at the axioms of projective geometry, there is no theory which has simpler axioms than projective geometry. Essentially, I might make a small mistake, but essentially the axioms are the following 3 axioms. The first axiom is that through 2 distinct points passes 1 line, and only 1. The second axiom is a line contains at least 3 elements. Okay. And the third axiom, which is a little bit tricky, is to say that, you see, if you have, you have 2 lines, A, B, and CD, which intersect, then the lines AD and BC intersect. Okay. Now, once you have that, and provided you are working in dimension strictly bigger than 2, there is a theorem. This theorem tells you that a projective geometry like this is a set of lines in projective space over a skew field. Over a skew field. And there is no reason to take a commutative field. In fact, Pascal, I think when he was 17 also, prove the theorem, and this theorem only holds if the skew field is commutative. So that's, but in general, there is absolutely no reason to. So the theory of skew fields is what is behind the scene in this H3, and it will, of course, later lead us to class field theory. And if you want, the obvious generalization of what was happening for the quaternions is the fact that this H2 here, it is, if you want, the cohomology, the second cohomology of the Galois group of Q bar over Q acting on Q bar star. Now, okay, so this, of course, is a very delicate theory a priori, but there is one of the greatest mathematical results which was proven by Brouwer, Hasse, and Eminater. I don't have the exact date, but I think it's 1933. And what they did, they completely classified the Brouwer group for this, so they completely classified this. And what is the amazing fact? The amazing fact is the following, what they proved. So they proved that if you take a skew field over Q, okay, call it K, so it's Q field. Okay. Now, what they proved is that then, this is a non-commutative field. Inside the skew field, there exists an ordinary field extension, L, included in K, commutative, an ordinary field, which is unramified on the thing. I mean, okay. So, I mean, once you have this type of result, okay, then you can, well, you have to, I am talking about the local situation, okay. So this is the local situation. And then you have to go from the global to local and so on and so forth. And what you find out is that when you write the exact sequence, which is here, with Cartier divisors, there is a global reciprocity law which holds because of the theorem of Noether and Hasse and Brouwer. Because of the reciprocity law, there is a missing Q mod Z. So in other words, when you write the long exact sequence, here you have an H2, okay, which is also a sum of Q mod Z. And so you have an H3 here, and this H3 is exactly the H3 of the spec Z with coefficients in GM, and it's a Q mod Z, okay? So that's where you are. All right, so after this calculation was done, okay, so as I said, this was in 1963, essentially, done by Artin. I mean, Emil Artin had a very important contribution in the Idele story because he computed almost the first examples, non-trivial examples. So once you know this, then there was an idea which was put forward by Mumford and Maser, which is the following. The idea is that if you think of spec Z as the three sphere, okay, and if you think in terms of schemes, well, in terms of schemes, what you have is that the prime number can be simply viewed as the map from Z to Z mod to Fp, if you want, which is taking integers mod P. So that's at the ring level. When you transpose that at the scheme level, okay, this gives you that spec Fp maps to spec Z. All right. And the idea is that, well, spec Fp, in which way can we think of this as a circle? Not quite, because we have to look at its fundamental group. The fundamental group of circle is Z. On the other hand, the Idele fundamental groups are never equal to Z because they are profinite. And when you look at the pi 1 of spec fp, what do you get? You don't get z, but you get z hat, the profinite completion of z, as generated by the Frobenius, which is the only natural thing to have. So in that way, you think of spec fp as a circle, okay? And you think of the transpose of this map as the inclusion of the circle in the three sphere. All right. Now, there is a very intriguing and interesting number that you get when you have nodes, if you want, which is the linking number of two nodes. Linking number of C1 and C2, where C1 and C2 are nodes. I mean, this number was already considered by Gauss, who defined an integral. I mean, he defined an integral which gives you this number. All right, I don't know what to dwell with this. But let's think about it in conceptual terms. Okay. So this linking number, when you want to define it in conceptual terms, you do the following. You say that what you have is you have the map C1. Of course, you don't want these two nodes to meet. So you map C1 to S3 minus C2. All right. And now you look at what this does on the pi 1. So we know, of course, that pi 1 of C1 is Z. Okay, so there is no problem. I orient C1 so that I know what is the generator. Okay, and now we want to look at what happens on the other side. Now, what happens on the other side, if you look at pi 1 of that, that's a very tricky thing. In general, it's already a very non-trivial invariant of the node, the pi 1 of the node complement. Okay? But what you can do easily is not compute this pi 1 of S3 of minus C2, but you can compute the abelianized fundamental group of S3 minus C2. Okay, and how do you compute this abelianized fundamental group of S3 minus C2? Well, you apply a very general result which is due to Hurewicz. Okay, so there is a theorem which is due to Hurewicz, and which tells you that the abelianized pi 1 is H1. And in fact, that was probably the origin of the reserves of Serre when Grothendieck was very excited by the étale site and all that, because it was clear that it would work for H1. It was not clear at all that it would work for either cohomology theory. Okay? And the reason why it would work for H1 was this theorem of Hurewicz, which tells you that this is equal to H1, H lower 1 of S3 with coefficients, sorry, S3 minus C2. Now, how do you compute this H1 of S3 minus C2? Again, okay? Again, a very beautiful general result. So again, a very beautiful general result. So the question is, how do you compute H1 of S3 minus C2? So H1 of S3 minus C2, okay. It turns out, so the result, if you want, it's due to Alexander and Pontryagin. And amazingly enough, it is on the occasion of this result that Pontryagin discovered Pontryagin duality. Okay, I mean, this is absolutely amazing because, so what this result tells you is that when you take the complement here of a node, but it could be a complement of anything inside S3, then what happens is that what you have to do, so here of course it's with coefficients in Z, okay. So when you pass to the complement, you have to change the coefficient to their Pontryagin dual. And the Pontryagin dual of Z is U1, so it's a circle, all right? So then what you do is you look, if you want, again, it turns out to be again an H1 of C2 with coefficients in U1. Okay, and that gives you U1, there is no problem. But now you have to take the Pontryagin dual of that, and that gives you Z. All right. So this is what Pontryagin and Alexander proved. This is the most conceptual form of it. All right. So now what you have at the level of the nodes, you have a map from Z to Z, because you have the pi1 of C1, which is Z, which maps to the abelianized pi1 of S3 minus C2, which is also equal to Z. So you have a map from Z to Z. In both cases, it's really Z, because I have chosen an orientation of the node, okay? And so what you have is you have an integer, all right? And then there are beautiful properties of this linking number. For instance, the fact that it is anti-symmetric. When you exchange the two nodes, it becomes the opposite, all right? Okay, and then you can play with it. I mean, there are plenty of things. Now, the analogy with number theory, with primes, is that, of course, we have now pi1 of spec fp, which we know, all right, which is generated by the Frobenius. And now what we do in order to remove a prime from the integers, this answers your question, okay? What you do is you take the ring Z. What does it mean that the scheme, you have removed the prime Q? It means that you invert Q, okay? So you take the ring Z of 1 over Q, all right? And now you have to compute its pi1 et al. But to compute its pi1 et al., now you enter into a deeper thing, which is that you have to look at those coverings of Z, which are only ramified at Q, all right? So you look, if you want, at covers which are only ramified at Q. Now, it's a very tricky thing. It's called wild ramification. And I mean, it is a story which has a lot of power. And what it gives you is that the pi1 is, in fact, ZQ star. So if you want, it's the invertible, the units in the ring of q-adic integers. Okay, I suppose you know what are q-adic integers. Okay, so they enter completely naturally here. And then you have to compute the map of pi1 of fp to this pi1 of the integers where you have removed q, all right? And now this computation is not difficult because of the fact that if you want, the action of the Frobenius is really raising to power p. And when you look at what it does on the wild ramification, it's exactly this. So in fact, it gives you the element p in ZQ star. So it doesn't give you an integer like the other one, okay? But what people say is that, well, then you can look at ZQ star modulo the square of ZQ star, so you can look at the Legendre symbol, okay? The Legendre symbol of P and Q, all right? And say that this Legendre symbol is the analogous of the linking number of the two nodes. And happily, you find that the Legendre symbol is antisymmetric when you exchange the two things, which is the reciprocity law. I am cheating a little bit because there is a modulo 4 business that you have to take care of, okay? But so this is the main idea. It's a very simple idea, okay? And I mean, the origin of my talks and the origin, if you want, of the joint work with Katia, which we published in a very small compte rendu note in the beginning of the year in January. The origin of the talk is the following, is that I didn't pay any attention to this analogy, but I knew that the Adele class space and the corresponding topos, which I will explain in my 2 hours tomorrow, had exactly a property which is, if you want, that it has in it circles corresponding to each prime, and these circles are canonically given. They are of length log p for each prime, and I mean, if you want, they are there at first very mysteriously, But the reason why they are so meaningful is the following, is that when you work at the level of adeles, at the level of class field theory and so on, what you find out is that it's not true that the primes should correspond to the points of a curve. No, because when you look at the triptych which I had described first, remember there were these three texts. When you look at the middle text, the text of the smooth curves over a finite field, so what one calls a function field, when you look at this text, it is not true that the places of the field correspond to the points of the curve. That's not true. The places of the global field associated to a smooth curve over a finite field correspond to the orbits of the Frobenius, not to points of the curve. So similarly, when we think about spec Z, we should have a little bit of imagination, and we should think that it's not the primes which are the points of the curve, no. Over each prime there ought to be a circle of length log p, which is the orbit of the Frobenius. And the Frobenius is now a one-parameter group. And this is what we shall see with the topos and with the adele class space and all that. And I remember at the beginning of the year, I heard a talk by Peter Scholz in which he was mentioning something like that. But then I realized that I had this space for years, and I had never looked at the way of the relation with the nodes. And as I will explain, the relation with the nodes is absolutely perfect. And we shall see that this picture, which is at first adelic through the class field theory, and then topos theoretic, thanks to the scaling site, will fit perfectly. Now, I just want to mention one thing, which is I got convinced by topos theory in 2014, which is late for a man of my age, okay? And the reason why I got convinced is that we had, with Katia Consani, and I had worked and I had found this adele class space, which is a very canonical and interesting space, which corresponds in the class field theory isomorphism to the schemes. And this space was understood at the time as a non-commutative space, very difficult, very interesting, very non-trivial space, as I will explain. But then, in 2014, we understood with Katia that this space, you see, the theory of toposes, for me, there are two major advantages over topological spaces. I don't talk about the étale site, which is one of the origin, but for me, one of the greatest advantage is that you can take a space and you can take a group acting on the space, or you can take a monoid acting on the space, which is much better. And then this is still a topos. It's no longer a space. Moreover, the theory of toposes tells you that when you have a topos, not necessarily a space, this topos has points. And in general, you look, and we shall see the scaling site. I can give you what it is. It's very simple to define. It's just one line. So what is a scaling site? It is the following topos. It is a space, which is the interval 0, infinity, semi-direct product with the integers, where the integers multiplicative act by multiplication. So that's all. But then you can take this topos and exercise, which is a bit difficult, compute the points of this topos. And you will see that the points of this topos form exactly the adele class space, which I had met long before. But when this was understood, it was clear that we could play on two grounds. We could play on the ground of non-commutative geometry, which is analysis, and we could play on the ground of topos theory, which is combinatorics, and which gives you a lot of mileage. And as we shall see, one of the mileage that we shall get is a structure sheaf of this topos. So we shall see what happens with the structure sheaf and all that. So I think I will stop here for today. And I thank you for your patience.